So let's ask a slightly more interesting question. Let's ask, does the sum from n equals 1 to infinity of sine n over n squared converge? Now, it might look like we've done this. Some of you will remember this was kind of a tricky problem that relied on the fact that the sine function is always between negative 1 and 1. And you might say, well, what's the difference between this and what we did before? But if you recall, when I constructed problems like this in previous sections, I was always very careful to write something like this or like this, because either putting absolute value bars around the sine function or raising it to an even power guaranteed that I was getting a positive number in the numerator. And as I've pointed out, the two comparison tests that we've been using require that the terms of the series be positive. They don't inherently work for series with negative terms. So in this case, we're going to take the series as it is. We're going to allow for the possibility that sine has some negative values, and I've put up a few of them. These are, of course, values of x in radians. The sine of 1 radian is 0.84, 2 radians is 0.91, 3 radians is 0.14. Then at 4 and 5 radians we get negative values. So it's not really like it's flipping back and forth positive and negative. It's just going to have some positive and some negative values depending on where we are in the circle. So, in the circle, as you go around the unit circle multiple times, that's what's going to determine whether the values are positive and negative. So, the point is we cannot, because the series has negative terms, we can't test it directly. But what we can do, very similar to what we did in the last example, is we can ask, does sum from n equals 1 to infinity of absolute sine n over n squared converge? So, we can say is that, first of all, the sum from n equals 1 to infinity of absolute sine n over n squared is equal to the sum from n equals 1 to infinity of that. That doesn't look like I've done very much, but what I've done is I've simply observed that I don't need the absolute value around the denominator because it's already a square. And what this is going to allow me to do is then make this argument that since the absolute value of sine n is between 0 and 1, that means that I can say therefore 0 is going to be less than or equal to the absolute value of sine n over n squared, which is going to be less than or equal to the absolute value of 1 over n squared. And this is, of course, going to allow me to use the direct comparison test. I can say, therefore, by the direct comparison test, the sum from n equals 1 to infinity of absolute sine n over n squared converges, and therefore by the absolute convergence test, sum from n equals 1 to infinity of sine n over n squared also converges. So we can conclude the proof that way. So so this is yet another use of the absolute convergence test, and in a slightly more interesting case.